Hi, I am Ramos de Miguel from the University of Las Palmas. I would like to thank all my co-authors in this work titled Finite Element Modeling, Evolutionary Optimization and Clinical Data for Personalized Cochlear Implant Stimulation Strategies. So the main topic of this talk today is about multiple stimulation, and it's important to know what is the current standard, which is monopolar. So we have one electrode active only to produce a hearing sensation. And in multipolar, we have many electrodes active at the same time. So you have normally one primary, one in the middle, and then all the neighborhood are playing a role, trying to steering the stimulus and trying to focus the stimulation as much as possible. So in our study, we have been able to try to generate the best focus multipolar profile. But we have to start from the very beginning, and we want to have a finite element method model that fits to real patient data. So we have an equation of Laplace, and this is a very simplified model that we have like a sphere that model the head, and then we have a reasonable cochlea, scala tympani, scala vestibuli, electrode in place, which is perimodular. It's the electrode of 512 from Cochlear, and then we generate the mesh. From this geometry, we have to define the cochlea, the electrode array, the reference electrode, that is this little one here. And then we have a set of virtual neurons, and then we define the boundary with a sphere with a radius of 20 millimeters. Then we have to define the electrical properties. So we have silicon that is a constant for the electrode array, and then we have these three per-lymph, bone, cortical, and exterior sphere, that there is a range of values, of valid values that can be selected depending on which one best match the transimpedance matrix for the model to a given patient. So I'm going to explain it now, but we have a transimpedance matrix from one given patient, and we have the transimpedance matrix generated by the FEM model. By playing with these three different electrical properties of the materials, per-lymph, cortical bond, and the sphere, we can match the transimpedance matrix of the model to a given patient by playing with these three conductivities. Then the condition, the boundary condition of the model, we have one for the electrode, which is the active one. Then we have the boundary domain, and then we have the reference electrode. It's important to consider here that all these transimpedance matrix matching from clinical data to the model, and also this simulation, it's in the domain of monopolar. So we want to fit the model in a monopolar space, and then we will move to multipolar. So this is one of the outputs that we obtained from the model. We use the differential evolution to have different set of conductivities for these three materials, and we finally get the best one that minimize the error between the clinical transimpedance matrix and the model transimpedance matrix. And the root mean square error in this case is 45 ohms in general, so it's quite accurate. But we have been thinking, hey, maybe we are missing data from the geometry of the cochlea. Could be a small or a big cochlea, and we are also missing information about the electrode position. It maybe not a fully perimodular electrode, maybe it's a lateral electrode, but we mislabeled this one. So we create different geometries with different electrode insertion, and we run again the whole system to find what is the best geometry, cochlear geometry, best electrode placement, and best conductivities in per-lymph, cortical bone, and the sphere that better match the clinical data that we have. So we have like an anatomical statistical modeling of the cochlea to make easy the formation of the cochleas. And at the end, we are able to get something better than before. So we have had into consideration geometry, electrode position, and also the three geometries, and the root mean square error now is 33 compared to the 45. It's not a huge change, but plays a role, and it's good to have as accurate as possible electrical model to keep playing or to keep having insight for what we are going to do now, which is multiple stimulation. So phase arrays, today the standard publication in literature on how to go for multiple stimulation. So we have a set of neurons, we have a set of electrodes, and the idea is to try to find a way to have volts, 1 volt in the central electrode and 0 volt at the level of the electrode and the rest. So we do that by changing or by inverting the transimpedance matrix, as Banner Hornet done in his publication. So if we calculate the current density that reached each of the neurons in this phase array, and we get the maximum current density, we can compare from monopolar to unipolar, and we see that there is a focusing of the stimulus. And from this data, we can create an objective function for focusing and for power. So we have this electrode and this neuron. So I want to have this electrode in the middle, the red one, to activate only the red neurons, those who are closer to this electrode. So this is like my objective function. I want to activate this neuron, but not the rest. So I want to activate N neurons, but not M. And this is my objective function, and this one is the power consumption from this given stimulation, multipolar stimulation. So we want to compare if one is better than the other one. So we could have this situation. We could have the blue one have a set of current to the electrode, and the other one, the orange one, have another set of current to the electrode that produce a channel, a multipolar channel, and that could be the current density along the neurons. We cannot compare them. It's really hard to see if one focuses more than the other one. So we need to normalize this data. So we decide to normalize this current for each of the electrodes divided by the maximum current density. And if we do that, we can compare how big or what is the amount of the area under the curve that we have. So we can have an estimation. We can have a metric to quantify if a model it's more focused than the other one. So we have basically a multi-objective problem. We use NSGA2 optimization scheme to find the best combination of current on the electrode to produce as focused as possible stimulus and as power saving as possible multipolar stimulation. And we get this result. For example, we have in monopolar in purple. Then we have the phase array, which is the gold standard today, the green one. We have in black the optimum focusing from this data that focus more than phase array because we are taking care of focus at the level of the neurons, not at the level of the electrode, and then our objective function. Okay, so in conclusion, we can say that the computational model combines trends and evolutionary algorithm to simultaneously optimize focusing and power in cochlear implants, and then the multi-objective optimization produces different current profiles for monopolar and for phase array stimulation in terms of focusing and power, and these solutions could be improved in terms of power and focalization if we take care of having that as goal, as objective target, the auditory nerve, and not everything at the level of the electrode. So again, thanks you to be here to participate in this meeting.